This is joint work with Yazmín, Ibáñez-García, and Magdalena Ortiz. And let me start by giving the main motivation of this work. So there are many challenges in trying to explore data sets. The first one is to build queries that match the user's information needs. And the second challenge is to try to refine those queries in such a way that they leverage the existing data. While ontologies help with the first problem in formulating queries, so for instance, if we take this small extract from the DPpedia ontology and we formulate this Sparkle query, when we evaluate it over the DPpedia, well, we see that this does not provide any answers. Well, in this case, the reason is because this Sparkle engine does not support any reasoning. However, in general, you don't have any guarantees. It might be that the data is incomplete and still the query does not have any answers. So applying a query refinement operation on this query. So in this case, we just simply change from settlement to city. We see that this query has answers. However, the problem is that we have to compute those answers from scratch each time. Now, there are many systems that try to cope with such problems. And if we try to categorize them based on ontological reasoning support for building queries and the expressiveness of the query language, we see that they split into two categories: those that do support reasoning, but the query language that they help construct is not so expressive. And the second categories are those that do not support any reasoning, but they aim for a more expressive query language. So we see that this coupling between reasoning and construction of conjunctive queries is not captured. So what is the general idea of our framework? Well, we want to generate a set of conjunctive queries which are mediated by one ontology. And then we try to exploit the containment relation between these queries in order to explore data sets. So for that, we identify this specialization and generalization relations between queries. So in this case, we call Q1 a specialization of Q2 and implicitly of Q3. And conversely, Q3 is a generalization of Q2 and also of Q1. So how do we formalize this idea? Well, for that, we define the notion of an exploratory query space. So let me first give you the preliminaries. So we are focusing ontologies formalized as DL T-boxes, and we later focus on DL light R. As queries, we focus on conjunctive queries, and an ontology mediated query is simply a pair of a CQ and an ontology. To formalize data sets, we consider traditional A boxes, and we do employ the certain answer semantics in answering OMQs. Okay, so what is a query space? Well, it consists of a set of queries which are mediated by one ontology and a preorder on the set of queries, which is a reflexive and transitive relation. And we call it exploratory for a given data set whenever the preorder implies containment of answers. So how do we navigate this query space? Well, intuitively here, we want to identify meaningful specializations and generalizations for given queries. So suppose that we have this specializing path that starts in Q, and we see that up to Qn, the set of answers does not change. And if we further specialize to Q prime, we see that the answers are strictly contained. So intuitively, in this case, we call Qn a maximal neutral specialization of Q, and Q prime is a minimal strict specialization of Q. So the more interesting ones are the minimal strict ones, because they are those that offer this gradual exploration of answers. But in order to compute those minimal strict specializations, we need to compute first the maximal neutral ones. So the challenge is to actually identify the maximal neutral specializations. So for that, we define this decision problem, which for two given queries in the space, the question is if one is a maximal neutral specialization of the other. So what we obtain is that this problem is going to be complete for a very simple setting when there is no ontology, when we consider CQ as a tree-shaped and the syntactic containment as a preorder. So analogously, we can define for the generalizing case. So how to build the meaningful query spaces? Well, the solution that we propose has three main components. So the first one is that the user provides a query template, which is simply a CQ in which atoms are marked with S for specializing or G for generalizing, and we can apply those to either concepts, roles, or individuals. The second component is a set of so-called reformulation axioms, which roughly is a small knowledge base in DLite R, plus some restricted form of complex role inclusions. And the third main component is how to apply such reformulation axioms onto the query templates in order to generate conjunctive queries. So one of the simplest rules is to simply apply the axioms from right to left. So whenever we have an atom that is marked with S, right? So in this case, we have event, which is marked with S, and we can specialize into conference. So we obtain a new query template. In the derivation process, we can at any step just stop and take the CQ, but let's suppose that we want to further apply the rest of the reformulation axioms onto this template. Well, because we use this restricted form of complex role inclusions, we are able to have operators that change from one constant to another constant. So in this case, we know that events located in roads are also located in Greece. So we can just simply change rows to Greece. And by dropping the markers, we obtain the CQ conferences that are located in Greece. And we have similar derivation rules for other reformulation axioms. So the nice thing about this approach is that we can encode it into a Datalog program, which we then evaluate over the data alone. And this will provide both functionalities to answer each query in the space, but also to navigate the query space. So let me give you just the intuition of the Datalog encoding. So we start by taking one Datalog constant for each template atom. And then we just simply keep track of all the reformulated template atoms. So for instance, here, as you have seen, we obtained that from first atom, we can reformulate it into conference. So how do we do that? Well, we just simply have a translation of the template into a set of facts, Datalog facts. Similarly, we also translate the reformulation axioms into a set of facts. And there is a very natural encoding of the derivation rules into Datalog rules. So this, for instance, this is the encoding for the first rule that we've seen. So the next step is to construct query atoms. And for that, we define a Datalog view, which simply tries to construct either a unary or a binary query atom based on the type of the predicate that we have derived. So afterwards, we define a view that captures each query in the space. So in this view this is the only rule that depends on the structure of the template. Okay, so how do we encode the previous query? Well, based on this view, we just simply have on the first position, we have conference, on the second, we have has location, and on the third, we have this. So basically, this represents the view-based rewriting of this query. So now how do we navigate this query space using Datalog? Well, intuitively, we just manipulate these query encodings. So for that, we first have to identify which are the strict operations on each atom. And to do that, we have to resort to stratify negation, because we have to test if there is some atom that is dropped by applying some reformulation axiom. So this checks if there is some reformulation axioms, and here we check if by applying it, there is some answer that is dropped. So then we identify those that are not strict. We infer that they are neutral. And afterwards, we transitively close this relation. And the maximal neutral operations, we also resort to negation in order to identify those. Okay, so now we move to computation of the maximal neutral specializations. And intuitively, here we iteratively apply maximal neutral operation on each atom. So we start from the encoding of the query, and then on the first atom, we apply a maximal neutral specialization. And then on the reformulated query, on the second atom, we apply another maximal neutral specialization, and so on for the other atoms. And lastly, the minimal strict specializations are obtained by applying on a maximal neutral specialization a strict operation. So this is the general idea of the encoding. We have also implemented and run some experiments of this encoding. So for that, we have used this rulework Java API for VLOG, which is a Datalog ± reasoner. As ontology, we have used DPpedia in DLite R. And as a reformulation axioms, we took a subset of the ontology and some data assertions, and in total, it amounts for 336. Now, as a data set, we have extracted relevant assertions from the DPpedia dataset, which are relevant for the signature of the reformulation axioms. And because we want to obtain certain answers for queries, we have also completed it with respect to the ontology. So for that, we have used these existential rules in VLOG, and the data was accessed via this DPpedia Sparkle endpoint.
Sorry, you have 2 more minutes.
And for that, we obtain in about 3 minutes 700 megabytes of data. So we use 5 query templates of different sizes and shapes over the signature of R. And this is what we obtained. So basically, the most expensive step was to compute the chase over the data. And for all the templates, the evaluation was done within seconds. This depends on the size of the generated query space. So for the largest query space that has about 360 queries, this was done in a bit more than 10 seconds. But once that this steps is done, then retrieving the answers and navigating the query space by computing this minimal strict reformulation, this is done very efficiently. So for all the templates, we obtain that this is done in less than 1 millisecond. So to sum up, we have proposed an abstract exploratory framework based on query spaces, and also have described how to generate meaningful query spaces using query templates. We have proposed a Datalog encoding of this approach and implemented and evaluated using VLOG reasoner. As future work, we would like to have an exploratory user interface to maybe consider other derivation rules such as dropping atoms, and to exploit the Datalog computed model for analytical purposes, such as maybe adding aggregation on top and see if there is any analytical functionalities that we can achieve. So thank you for your attention, and if you have questions.